Hello, everyone. My name is Tom Helmuth, and today I'm here with Bill Cava. And during this tutorial, we're going to give you a deep dive into Lexicase selection. We're going to be talking about the Lexicase selection algorithm, how it works, places it's been used, the reasons that it works well, and just give you a general idea of how you could use Lexicase selection in your work. So to get us started, Bill is going to give us some background about the stuff you need to know in order to use Lexicase selection.
Thanks, Tom. Yeah, so let's start with some background and motivation for why we want to do Lexicase selection. And I'm going to assume that most of the audience members here are familiar with evolutionary computation, but just in case you're not, let's step through a basic version of what evolutionary computation systems look like. So Lexicase selection is a parent selection technique that you use in evolutionary computation. And in order to understand what that means, let's look at the basic steps. So this is not going to cover every evolutionary computation system, but in general, what we have is a system where we initialize a population with random individuals that are candidate solutions to our problem. Here we're showing those individuals as bits of code, which is how genetic programming represents individuals. And in order to evaluate how well those individuals solve the problem we're trying to solve, we do a fitness evaluation. And importantly, when we talk about Lexicase selection, we're interested in fitness evaluations where an individual is evaluated on a set of training cases or objectives. Now, if we find an individual in the population that solves our problem perfectly, we might stop, but otherwise, we're going to step through stages of parent selection, where we select individuals from the population that are the most promising, and we apply some variation operators to those parents in order to produce offspring, and then loop through this process, evaluating fitness, selecting parents, and tweaking them until we reach a solution or converge. So let me talk about some of the nomenclature that's used in this tutorial and in evolutionary computation research. So what we have here is a supervised learning problem where we have training data, which consists of paired examples of inputs and outputs that we want our system to learn from in order to map those inputs to new outputs in the future. So we have the training data, which is great, this gray table here, and each row of that training data is a case. And that is the case in Lexicase selection that we usually use. So you can think of cases as being samples of training data. And then what we have are individuals who have semantics. So semantics are the behavior of a genetic programming program on the training cases. In the case of genetic algorithms, typically the semantics and the syntax or the genome of each individual is actually the same thing. We evaluate the genome directly in order to assign fitness. In genetic programming, it's a little different because we execute that tree or that program structure in order to produce behaviors. Now that we have training data and semantics, we can combine those each generation to get an error matrix, which we simply call errors. So this matrix on the bottom shows for each case and for each individual, which is in a column, how its behavior corresponded to the target value for those cases. And along the bottom, you'll see a total error. This is typically, what we'll use to guide evolution in systems other than Lexicase selection is some aggregate fitness. But as we'll see with Lexicase, we don't need to aggregate. And actually, we would prefer not to aggregate these errors.
Before we get on to sort of how Lexicase selection works, I want to give you some backstory of the motivation so you can get an idea of what are the types of situations where Lexicase selection can be useful. And so to go back to its origin, our colleague Lee Spector was for a long time working on a particular problem in genetic programming of trying to evolve a program to replicate the behavior of a push button calculator. And so this has a variety of interesting ideas that you need to consider in order to try to replicate this behavior. But one really interesting part of this is that there's going to be a variety of different test cases or training examples that represent different pieces of the calculator. And so, for example, perhaps you want to have some training cases that are explicitly trying to test whether the program correctly performs multiplication when using the multiplication key. Other cases will test whether you're doing division correctly. Other cases will test addition, and so on and so forth. And so these sort of different cases represent different behavior that a program has to encode in order to fully solve the problem. Now, this even gets more finely grained than that. So one specific example that Lee was considering is when you are doing division, sometimes with division, you need your program to just divide the two numbers and return the answer. But you probably want to do something completely different if the program is trying to divide by 0. If you have an example of an input where the result is a division by 0, the calculator might treat that entirely differently than it does normal division. And so even with the same or very similar inputs, you can have wildly different behaviors that you want your program to encode. And so Lee was thinking of these as very modal problems. And in other words, you need a program that has different modes of behavior depending on what your training data is. And so along those thoughts, he was trying to figure out, okay, if I just run my program on this variety of example data, find errors for each case, and then sum those errors into one total error, I'm going to be forgetting programs that have figured out certain parts of the problem. So for example, maybe one program has figured out how to do multiplication correctly. Another has figured out division in general, but not the division by 0 case. And maybe you have one program that's figured out addition and division by 0, but does really poorly on other, multiplication and subtraction, for example. And so if you are just considering the total error, you're sort of not paying attention to which individuals in the population are performing well at different parts of the problem. In fact, an individual that has solved a particular part of the problem, its genes might not be selected at all if it has an overall poor total error because it hasn't figured out how to solve other parts of the problem. And so the key motivation here is that in many cases, we want to be able to emphasize programs, or in general in evolution computation, emphasize individuals that do well at some parts of a problem, even if they don't necessarily perform well at all parts of the problem. And so with this in mind, I want to talk more generally about the motivations here. I've mentioned a bunch of these things already, but I want to go into a little more detail. Most parent selection methods, let's take tournament selection as an example, use a single aggregated fitness value. That is, each individual has one fitness value that represents how well that individual performs, no matter what your evaluation otherwise is. So for example, even if you are evaluating a program across many cases, you'd only look at the total error across all of those cases as your fitness value. Now, I do want to mention that even multi-objective methods such as NSGA2, if you're using that where total error is one of your objectives and something like program size is another objective, or methods such as quality diversity methods, these tend to aggregate errors into a single fitness value. Now, as I mentioned, for some types of problems, and as it turns out, we're going to talk about how this seems to be important in a huge variety of problems, that this obscures useful information about how a program or an individual performs. And so I'm going to look at a brief example here. Let's imagine we have an individual who we will call Q. And let's imagine that Q performs well on some cases and poorly on others. And so pictorially, I have this here as the Q has a good fitness on, we just have 6 error values here. Let's say it has a good error value on the 4 errors where we have light gray boxes, and poor error on the 2 with dark gray boxes. Now, it's certainly possible that Q has found some sort of genetic material that's worth propagating to children, but because let's imagine that Q performs really poorly on the 2 cases that it performs poorly on, it's not likely to have a good total error, and therefore, sort of in comparison with other individuals in the population, it's not likely to be selected by a parent selection method such as tournament selection. And so this skill that Q has come up with, that's figured out how to do something good, could be lost in the population. Now, this has to do with an idea that we're going to talk a bit more about later, which is the idea of specialists and generalists. I would call a specialist an individual that does really well at some parts of a problem and poorly at others, where a generalist performs okay at all parts of a problem, not necessarily sort of exceeding other individuals at any one part of the problem. And so by selecting individuals that do well across the board, we tend to select generalists. Now, the one other piece of motivation here is in semantic-aware selection. And so this is an idea that was sort of brought to light by Chris Kravich. And that idea is that we perhaps want to do selection in a way that does not aggregate errors into a single fitness value, because this aggregation of errors creates what he calls an information bottleneck, where you have a variety of information of how an individual performs across a number of cases or objectives. And if we aggregate this information, this reduces our information to a single value. And as we'll see, Lexicase selection does not do this. It does not take all of our information across cases and put it into a single value. Instead, like other semantic-aware selection methods, it makes use of individual semantics or error values. It does not sum them up or in any other way aggregate those errors. Okay, so that gives you a lot of background about the motivations for Lexicase selection. The next thing that we're going to talk about briefly are places where Lexicase selection has been used, so that we can give you some ideas about places where it has been useful and might continue to be useful in the future. And then we're going to dive into the details of how the Lexicase selection algorithm works. So to start off, I'd like to talk a bit about program synthesis. This is an area both in genetic programming and more widely in machine learning, where you want to try to generate a program that solves a problem by using multiple data structures, control flow structures such as conditional execution, loops, recursion, those types of things. And so in this problem area, Lexicase selection has outperformed many other selection methods in different experiments. I'm showing you one example here from the original publication of a benchmark suite of program synthesis, but across many different types of problems and with different GP systems, Lexicase selection is shown to be much more effective at solving problems than tournament selection, as well as a variety of other parent selection methods.
So you might think that Lexicase selection might be specific to very difficult multimodal problems in program synthesis or the calculator example, but we've also found it to work very well for regression problems, where there also is multimodal behavior in the problem space. So for these types of problems, we needed to introduce a variant of Lexicase selection for floating point values, which we'll talk about in this tutorial. It's called Epsilon Lexicase selection. But the important thing to note right now is just that it's been shown to outperform many state-of-the-art genetic programming techniques, as well as a number of machine learning techniques for regression. So here we're looking at a result from our 2018 GECCO paper, Where Are We Now?, where we benchmarked a bunch of different symbolic regression and machine learning methods on hundreds of regression problems. And what we found is, Epsilon Lexicase selection worked really well and performed on par with, gradient boosting and other ensemble tree-based methods, as well as multi-layer perceptrons. And so this was an indication that this technique, this method, has wider applicability than just in program synthesis. And we have looked at other areas as well. So another area that has a kind of theoretical tie to Lexicase selection is multi or many objective optimization. Many objective optimization usually refers to multi-objective problems with many objectives, so anywhere from 3 to 100 or more. And this is an important class of problems that is heavily researched in the evolutionary computation community. And what we've found on some basic kind of benchmark problems in this area is that as the number of objectives increase, Lexicase selection, where the cases are defined as objectives, actually performs really well, performs on par with other methods in this area. The graph on the left here is showing the probability of selection for different individuals in the population for a 3 objective problem. And we're going to talk about that later in the talk, what selection probabilities are under Lexicase and how those can be understood through a multi-objective lens. Another area where Lexicase has been used is evolutionary robotics. So here, there's been some work to use Lexicase selection as a way of rewarding different behaviors that are desired in the simulation. It's been used for quadruped animate evolution and has been shown to outperform some other selection methods. We've also found it to work well for soft robotics when evolving locomotion. And the idea here, tying back to the deaggregation idea, is that instead of rewarding a robot for its movement from the origin over the entire simulation, we deaggregate the time steps, and we are rewarding each robot for how much it's able to move at each of those time steps. And so this gives you a much richer idea of how the robot is behaving over the course of the simulation that you otherwise would not be able to get just looking at the aggregate behavior. So that's a few areas where it's being used. There's a number of other ones. Boolean logic and finite algebras problems have been tackled using Lexicase selection with genetic programming. We've also seen it used in learning classifier systems and in Boolean constraint satisfaction using genetic algorithms. So we think that Lexicase selection has a pretty wide applicability to different evolutionary computation systems. And it's based around a pretty simple algorithm that we'll describe right now.
Wonderful. So now that you've seen different areas where Lexicase selection has been applied, we're going to go through the algorithm in detail to give you an idea of how you'd go about implementing this. We're going to be sort of walking through this step by step, since this is sort of a really important piece of this tutorial. The first thing I really want to mention is that each Lexicase selection selects a single parent. So this process that we're going to be conducting is going to be used once to select one parent, and then to select another parent, either for crossover or if you need another parent to create a new child, then you'll run this entire algorithm again. And so the Lexicase selection algorithm starts by taking the entire population. we're going to call that the pool or the selection pool. The way that the Lexicase selection algorithm works is that we're going to be starting with the entire population and whittling it down to either a single individual or small number of individuals by the end of the algorithm. And so that's that pool. And the other important piece here is that we are going to take our list of training cases and we're going to shuffle it uniformly into a random order. And we will call this cases. As we will see, this step of the process is the only random part of the entire algorithm. And so this is the step that is going to allow Lexicase selection to select different individuals in order to have a diverse set of parents. Now, the next up, we're going to run through this while loop. As long as the selection pool has more than one individual in it, and our list of cases has at least one case in it, what we are going to do is we are going to first look at the first case in our list of cases. So we'll call this case T. And then we are going to look at our current pool of individuals and figure out which of those individuals has the very best error value of any individual in the pool on case T. So whatever this best error value is, we will call that best. Now, a bit later, we'll talk about how you might want to relax that in certain situations. But for now, we're going to assume that you want the very best error value of any individual in that pool. Now, the reason we're going to do that is then we're going to take our pool of individuals and we're going to filter it so that it only includes individuals that have that best error value on case T. So in other words, after this step, the pool will only include individuals who tied for having the very best error in the pool on this case T that happened to be first in our random shuffling of our cases. Finally, the last part of this loop is that we're going to pop T from our list of cases and repeat. And so the next time through the loop, we'll be looking at the first case in our list of cases. We'll be finding the best error on that case. You'll note that that best error is in relation to, relative to the current selection pool. So if the individual with the best error in the full population isn't in the pool any longer, because it was filtered out at an earlier step, we will only be finding individuals with the best remaining error. And then we'll go through the filter process over and over again until one of two things happens. Either, once this while loop ends, either our pool is reduced to a single individual, and at that point, we know we have one individual who had the best error on the first case, or at least tied for the best error on the first case, had the best error of any remaining individuals in the next case, and on the next case, and on the next case, until only a single individual remained. And therefore, this individual is good at least some of the cases that we are considering, or some of the objectives, and we're going to return that individual as the selected parent. Otherwise, the other way that this loop can end is if we go through all of our cases and we still have more than one individual left in the pool, at which point we know that all of those remaining individuals tied on all of the cases that we considered, so we have no other information to differentiate between them, and so we can just return a random individual from that pool, knowing that that individual was at least best in the population on each case that was considered. So that gives you an idea of the full Lexicase selection algorithm. And next up, I'm going to go through a few examples of running Lexicase selection on a small population with a small number of training cases, just so that we can see Lexicase selection in action. And so I have created this artificial population here that has 5 individuals in it, individuals A, B, C, D, and E. And we also have 5 cases that each of these individuals has been tested on, 1, 2, 3, 4, and 5. And so for each of these 5 cases, we have our error values for each individual listed in this table. Now, before we think about Lexicate selection, let's think about how something like tournament selection that considers total error would consider this population. With this small population, tournament selection would certainly have the best chance of selecting individual B, followed by A, followed by D, and individuals C and E would be unlikely to be selected very frequently by tournament selection. Now, of course, this population is much smaller and the number of cases is much smaller than we typically use for an evolutionary computation, but wanted to give you a small example so that we can see how this works. But one last thing before we look at some examples, I do want to briefly mention, if we look at individuals A and B, we'll notice that they tend to have errors that are overall pretty good, overall not best in the population. Many times there are errors that are better, but these are what I would consider generalist individuals that perform pretty well across all of the cases, but not super well at any one case. Where individuals C and E, and to a lesser extent D, have certain cases that they specialize in, that they perform really well at, and other cases where they perform rather poorly. And so that's going to come into play when we look at what individuals are selected by Lexicate selection. And so let's look at an example. Let's imagine we are running Lexicate selection and our random order of cases happens to come up 5, 2, 1, 3, 4. So let's run through what happens each step of the way as we go through here. So first up is case 5. And when we look at case 5 with this population, we're going to see that the best error in the population is 1 on this case. And so 3 individuals, C, D, and E, happen to have that best error. They all tie. And so they're going to survive and to be filtered to the next step of Lexicase, where individuals A and B have worse errors and therefore are going to be eliminated. So next, when we look at case number 2, first of all, it's really important to note that the best in the pool is only relative to the pool. And so even though 12 isn't the global best error, because individuals A and B have better errors than that, they have already been eliminated. And so therefore we are only looking at C, D, and E. And of those individuals D and E have the best error tied at 12, and therefore will continue on while individual C will be filtered out. At the next step, we look at case 1, and we see that individuals D and E are actually tied on case 1. And so at this step, we aren't going to filter out either of them. And then at the next case, we look at case 3 and see, when we look at case 3, we see that individual E has a better error of 0 than individual D's error of 14. And therefore individual E will be selected, or will be the only one remaining in the selection pool, and therefore will be selected. So individual E will be returned. So this has given you one example of one case ordering, but to really see how different case orderings can result in different individuals being selected, we're going to look at 2 other brief examples. And so for example 2, when we look at having case 1 come first, you're going to see, interestingly, on case 1, individual B has an error of 8, and no other individual ties with individual B on case 1. And so therefore, individual B will be returned immediately, and all of the other individuals will be eliminated. Now, you might wonder, okay, is this something that happens frequently in Lexicate selection? I will tell you it happens occasionally when you have an individual that just happens to be better than everyone else at a certain case. But it doesn't happen all of the time. We typically see at least a few cases, if not 10 or 20 being used per selection event. We're going to look at that a bit more later, but it does occasionally happen that a single case can determine what individual is selected. Finally, now let's look at one third example. Let's look at a case or an ordering where case 3 happens first. When we look at case 3, we see that individuals C and E tie for best with an error of 0. All other individuals are eliminated at that step. When we look at case 5, we see that C and E tie on case 5, and so they both continue to the next step. And then, oops, one slide too far. There we go. Then we look at case 4, and on case 4, we see that individual C performs better than the other remaining individual E, and therefore is returned by Lexicase selection. And so, after looking at those examples, I want to talk briefly about when Lexicase selection is applicable. Because we want to be thinking about what are the cases where you would use Lexicase selection, and when is it just something that you cannot use. And so probably the most important thing here is that you need to have a fitness that either is already decomposed or can be decomposed into its component parts. So for example, if you have a variety of cases or objectives that you can use as different measurements of performance, then that's certainly a place where you can apply Lexicase selection. However, if you have just a single fitness value, so for example, if you have a problem where you have a single output, or if you have sort of a black box optimization situation where you only get an overall fitness value of an individual, you can't really apply Lexicase selection because you don't have multiple cases or objectives on which you can apply it. The other consideration here is that you need to make sure that you have enough components or cases or objectives in order to judge fitness. So the way that I like to think about this is that there are a factorial number of different ways you can shuffle the cases based on the number of cases. And so if you have n cases, then you'll have a factorial of n different ways that you can shuffle those cases. And the number of different ways you can shuffle the cases determines how many different error vectors individuals can have who are selected. I'm not going to say that number of different individuals, because if 2 individuals have the same error vector, then they could be selected with the same shuffling. But if you have a small number of cases, let's imagine you have 4 cases, then you're only going to have 24 different ways you can shuffle the cases. And so at most 24 different error vectors that could be selected in any given population. So that doesn't really seem like much. Say if you have a population of 1,000, I could imagine that wouldn't be enough to be effective. Now, even if we just go as high as 6 cases, then you're getting 720 different shufflings of cases. And I could certainly imagine that being much more reasonable. General rule of thumb here is if you have, say, a little more than a handful being 5 to 7 or so, then you probably have enough cases in order for Lexicase selection to work. The other thing I want to mention right now is who gets rewarded by Lexicase selection. After looking at the algorithm and looking at some examples, it should be clear that individuals that are sort of good at some cases, especially very good at some cases, and specifically cases that other individuals are not good at, are those that tend to be rewarded by Lexicase selection. Now, that doesn't mean that individuals that are really good at a lot of cases won't be rewarded. In fact, those will be rewarded more. But if you have a population where how good individuals are is spread sort of evenly between cases, those individuals that are perform really well at certain cases, when those cases come up early in the shuffling, they will then be rewarded and will be selected, as opposed to individuals that perform okay, but not great at all cases. And so again, we'll talk more about generalists and specialists later, but this is related to those ideas. I'm going to pass it off to Bill, who's going to talk about Epsilon Lexicase.
Great, thanks, Tom. So we've talked about Lexicase selection, and I know in one of those examples, example 2, Tom mentioned that, occasionally with Lexicase selection, you can get a parent selected on a single case, but most of the time you're going to use multiple cases. And that is true for Lexicase selection applied to integer and applied to Boolean type error matrices. However, we introduced Epsilon Lexicase selection in order to handle the floating point situation where you have an error matrix made up of floating point semantics. So when you're working with floating point semantics, it's much less likely that you're going to have ties on any particular case. If you think about it with floating point values, there's many different values a program can take for a specific output. And so this can lead to very shallow selection events when you're using Lexicase selection. To remedy this, we came up with Epsilon Lexicase selection, where the epsilon, as you might have already guessed, is a relaxation on this filtering step. So instead of only allowing individuals through at each Lexicase selection step who are the best on that case, we let any individuals through that are within some epsilon of the best, and any individuals outside of that epsilon are filtered out. So this relaxes the selective pressure at each step of Lexicase selection, and also, allows us to still select individuals that are doing very well on specific cases. How we define epsilon is something we've studied a bit, and we've come up with a couple parameter-free definitions of epsilon that are based on the statistics of the population. And I'm going to go over those now to give you a sense of how they differ from the kind of baseline Lexicase selection algorithm. So with Epsilon Lexicase selection, I've highlighted here basically the only line that is different when compared to the standard Lexicase selection algorithm. And what we're doing in this line, which is 3C within the while loop, is we're calculating an epsilon that's based on that specific case and the population behavior on that case. So what we discovered is that using the median absolute deviation of the population's behavior on that case works pretty well as a definition of epsilon. We refer to this definition as static epsilon Lexicase selection. And it's important to note that we don't need to recalculate it within this while loop. Actually, we can just calculate it for all of the cases prior to selection, so once per generation. But this gives us a measure of essentially how closely distributed the population's behavior is to the best performance on each case. Now, we've also looked at other ways of defining epsilon. And one of those is to instead define it dynamically. So rather than doing it once per generation over the whole population, we could define epsilon as the median absolute deviation of the current selection pool on that case. And in this case, epsilon is going to vary depending on which individuals are in the pool. And so it's affected by the ordering of the cases when you start selecting a parent. And what we found, at least for regression problems, which is where we mostly apply this algorithm, is these two definitions don't give you very different performance. And since static epsilon Lexicase selection is a bit faster, we only have to calculate the epsilons once per generation. We tend to go with that version in our implementations. But as far as we know, these perform pretty similarly. So epsilon Lexicase selection is kind of an optimization, I suppose, of Lexicase selection for floating point problems. But there are other optimizations and tricks that are commonly used with Lexicase selection. And now we're going to talk about a few of those that you might want to consider if you're implementing Lexicase selection in your system. So one that's heavily used, especially with the baseline Lexicase selection algorithm, is pre-selection filtering. So the premise here is that in genetic programming, programs will often produce the same error vector as other programs. So imagine these two individuals in the graph on the right here. I'm sorry, the table. Individuals A and B, they have the same semantics for each case in our training data. we refer to these as equivalent or in the same, belonging to the same equivalence class. So if two or more equivalent programs make it to the end of a parent selection event in Lexicase selection, basically we've just discovered that they're the same, but we did so in a way that required us to look at every case and filter individuals in every case. So since it's much easier to determine beforehand whether individuals are equivalent, we can make Lexicase selection more efficient when handling multiple copies of the same semantics by doing some pre-selection filtering. So the idea here again is Lexicase selection has some inefficiency if you have identical semantics in your population. And so in order to make Lexicase selection stop earlier and not get to this kind of worst case complexity, which we'll talk about a little bit more in a few minutes, we want to filter down to just unique individuals. So this is the algorithm that has been come up with to handle this. So we're going to group individuals into equivalence classes based on their error vectors. We can do this once per generation. And then we just run Lexicase selection on these error vectors that, one error vector from each equivalence class instead of running it on all of the individuals. At that point, after we've run Lexicase selection and we've picked an error vector, we can associate that error vector with the equivalence class it comes from and then select a random individual from that equivalence class. And you'll note that this kind of corresponds to the last step in the Lexicase selection algorithm where we're choosing randomly from individuals left in the pool. And in fact, if you do this pre-selection filtering, there's no functional effect on the results of Lexicase selection, which is what we want. And that means we have the same probability of selection for every individual, even though we've done this pre-filtering step. This can provide a substantial speed up of running times because, as we'll see later on, the worst case complexity of Lexicase happens when the entire population is tied, right? So when the semantics are equivalent, we basically never eliminate individuals from the selection pool by going through the cases. And so if we first identify those individuals that are clones, we do see substantial speed ups of running times. The one place that pre-selection filtering is not functionally equivalent is when we talk about dynamic Epsilon Lexicase selection. So as I mentioned earlier, in dynamic Epsilon Lexicase selection, we're calculating Epsilon on the fly within each pool as we're doing filtering. Because of that Epsilon is going to depend on what individuals are in the pool. And if you have tied semantics, you're going to have multiple copies of individuals, and that will shift the distribution of semantics and therefore change Epsilon. So that's an important thing to note. If you're using static Epsilon Lexicase, you don't run into that problem. But another point that we should note is when you're using Lexicase selection or Epsilon Lexicase selection on floating point semantics, there's going to be fewer ties in general. And so this optimization trick of pre-selection filtering is really most effective when you're using the standard Lexicase selection algorithm. You might have also been thinking about the fact that when we run Lexicase selection, we don't actually necessarily look at every training case, right? Sometimes we end early. Sometimes we only have to look at a single case in order to do a parent selection. So couldn't we use lazy evaluation as a way of speeding up Lexicase selection versus other, evolutionary computation approaches? The answer to that is yes, you can, but the kind of benefit you're going to get from doing this lazy evaluation really depends on how many training cases you have and how many cases you have relative to the number of selections you're going to do. So the graph on the right is illustrating this equation on the left. And what this equation on the left is showing you is the value of T, the number of training cases, relative to the number of selections you're doing per generation. And this inequality describes when every case that you have in your training data is more likely than not to come first in a selection event in a generation. So why do we care about that? We care about that because recall that the first pool going into every parent selection for Lexicase contains the whole population. And so the first case in that shuffling needs to be evaluated on every individual. So you can imagine if you have n selections per generation that each start with a different random case, lazy evaluation will only help if each case has a low probability of coming first in that generation. Otherwise, we might as well just evaluate all of the individuals on all the cases, not bother with the lazy evaluation scheme. If you graph this equation basically on the right here, we get a probability of a case coming first. And you'll see when you have lots of training cases relative to the number of selections you're doing in the blue area, you're saving a lot of time actually by doing lazy evaluations. If instead you're on the kind of right bottom part of this graph where it's red, the probability of every case coming first is quite high, and therefore doing lazy evaluation isn't going to help you too much. So in addition to those optimizations and tricks, we want to talk a little bit about different ways of interpreting Lexicase selections behavior. So one way to interpret it is as a multi-objective optimization algorithm, which I mentioned a little bit earlier in this tutorial. And so you might wonder, with respect to multi-objective optimization, what kinds of Pareto guarantees do we get with Lexicase selection? Well, one thing that's pretty interesting about it is if you think about Lexicase selection as operating on objectives where objectives are your training cases, then you can actually pretty easily prove that Lexicase selections are Pareto optimal with respect to those cases. In other words, individuals that are selected are on the Pareto front that's defined by your training cases. So on the right here, I'm illustrating Lexicase selection with a case sequence of training case 1, training case 2. The y-axis here is the error on the training case 1, and the y-axis is error on training case 2. So here I'm showing different individuals in the selection pool. Some of them are circles and some are squares. So the reason that some are circles and some are squares is because the squares represent individuals that are Pareto optimal with respect to the training case. Now, what that means is if you select any individual on that Pareto front from this Pareto optimal set, you cannot find an individual in the population that is as good as or better than any of those Pareto optimal individuals on one of the training cases without also accepting an individual with worse performance on the other case. So in that sense, they're kind of pure trade-offs between the error in these two cases. So in this selection event I'm showing here, the first filtering step of Lexicase selection picks this outer rectangle. So we're filtering on E2, E1, and that means we take these two individuals that have the best fitness on E1, on training case 1. Then in the second step, the second filtering step of Lexicase selection, we select on E2, and that gives us the individual shown in black, the black square here. And that would be the individual returned as a parent by Lexicase. There's another black square down towards the bottom of this graph, you'll notice. That black square corresponds to the individual selected from the opposite sequence of cases. So in another parent selection where T2 comes first, we would select that individual. One thing that you'll note is for these two sequences of cases, we're not selecting any old individual from the Pareto front, right? We're selecting those that are on the boundary. And this is another important aspect of Lexicase selection in a multi-objective context. It is going to select individuals on the corners rather than the knee of the Pareto front. So these three individuals in the middle that are, as Tom has kind of referred to, basically generalists between these two cases. Those won't get selected by Lexicase. Lexicase selection is interested in the individuals that perform really, really well on cases or subsets of cases relative to the population. And what that translates to in multi-objective optimization is selecting the corners of this Pareto front. So now let's look at what this looks like with Epsilon Lexicase selection. Things are a little bit different here. So in this case, we're not just selecting individuals from the Pareto front. Instead, we're selecting individuals from what is referred to as the Epsilon Pareto front. So if we were to define an Epsilon Pareto front that has a little bit more of a loose definition of Pareto optimality, where we accept all individuals within Epsilon 1 and Epsilon 2 of the front, then we get these models that are kind of shown as dotted lines as included in our Epsilon Pareto boundary. If we define that boundary, then we can basically say the same thing about Epsilon Lexicase selection that we say about Lexicase selection, which is that it selects individuals that are within Epsilon of the Pareto optimal points and within Epsilon of the corners. So if we look at the same sequence of cases here, our first selection is going to give us these 4 individuals here. And those 4 individuals are within Epsilon 1 of our best performance. So that gives us this outer rectangle. And then in the second step, we're going to select individuals that are within Epsilon 2 of the best model on error 2. And so that gives us this black square, which you'll notice is not at the corner of the Pareto front anymore, but is actually biased inwards. And that selection really depends on the size of Epsilon 2 here, right? So if Epsilon 2 extends to the edge or the corner of the Pareto front, then we could randomly select from among these models. But in general, what we're doing is we're biasing selection towards the knee relative to Lexicase selection. And that's going to give us slightly more general models than we would get using baseline Lexicase selection. And depending on whether or not that is good for your problem, this can be good or bad. What we found is that it works pretty well for regression. Just to push this point a little bit further, we've looked at Epsilon Lexicase selection as a many objective optimizer, and bringing it back to this slide, which we showed earlier. If you look at the selection probability under Epsilon Lexicase selection for a problem with 3 objectives, which we're showing here, you can see the same kind of pattern where we're selecting individuals that are near the corners, but slightly moved inwards when we do Epsilon Lexicase selection. So these individuals shown in blue, these are the ones that are going to be selected to be parents. Now, every point on this surface that's shown here is Pareto optimal for this problem. That's what we're illustrating is the Pareto front. And so again, it's important to know that Epsilon Lexicase selection does not give you any Pareto optimal points. There's very specific ones that it's biased towards, similarly with Lexicase selection. However, when we look at many objective problems, we run into the curse of dimensionality. And what that roughly means is that basically any random point in your optimization is going to very likely be Pareto optimal, and they're all going to be pretty far apart. So you can think of Epsilon Lexicase selection as one type of assumption about which points are worth propagating, which are those in these high dimensional multi-objective spaces that are somewhat pulled towards the best performance on individual objectives, right? And so we've seen for certain problems we've looked at that this is a good way of biasing search in that we get better convergence measures and better actual spreads along the Pareto front using Lexicase than we would get with other optimizers in this class of methods. So those are some of the optimizations, tricks, and interpretations. I'll hand it over to Tom to talk a little bit more about why Lexicate selection works.
Yeah, so we've put a lot of research into thinking about why Lexicate selection works. As we mentioned very early in this tutorial, it has shown to perform very well in a large variety of problem domains. And so I'm going to talk about some theories that we've come up with. I think there's certainly still more work that needs to be done in this area, and work that that certainly others have done as well is going to contribute to some of the things we talk about. But I'm going to try to go through some of the ideas behind why we think Lexicate selection works. And so to start off, I want to touch on one point that I've brought up a few times now, which is this idea of specialists and generalists. In order to be a little more specific about what we're talking about here, I want to define a specialist as an individual that performs really well on some parts of the problem. This might be on some of the training cases. I'm going to use the word case here, but this could also be if you have multiple objectives on some of the objectives. And on the other hand, this individual is going to have relatively high errors or perform poorly on other training cases. Now, because of this, this individual likely has a poor total error or aggregate fitness relative to the rest of the population. And so I have an example here of an individual that has relatively good error on 3 of these cases, relatively poor error on 6 of them, and a total error of 49. Now, let's compare this with generalists. Generalists are individuals that perform similarly on all training cases. They might not optimize really well any one training case, so they might not perform all that well on any particular case, but they don't perform particularly poorly on any case either. Now, these individuals tend to have relatively good error compared to the rest of the population. And in this example here, we have an individual that has no errors that are sort of really good, 0 or 1, but has pretty good, decent errors across all other training cases for a better total error than the specialist. And so it's certainly an open question of, do we want to select specialists during evolutionary computation? Will they drive the search better, or will generalists drive the search better? Will those lead us to better and better solutions? And so my interpretation of Lexicate selection, we're going to talk a bit more about the difference between where, say, tournament selection and Lexicate selection put their emphases. But the good performance of Lexicate selection certainly makes me think that the specialists that we see Lexicate selecting are really important because they allow it to look in different areas of the search space. They allow it to, as we're going to see, maintain higher population diversity while putting significant selection pressure, right? We're not completely abandoning objectives like something like novelty search, but instead we are putting selection pressure on doing really well on some cases, but not necessarily having to perform well across all cases. Okay, and so in order to look at this a bit more, I want to look at the idea of which individuals are selected by different selection methods. And so, as I was just mentioning, empirically, it seems like specialists are better to select in many cases. But let's think about what types of individuals, in this first example, tournament selection selects. Now, let's imagine we have this population that's graphed here, where the x-axis is an individual's rank in the population when sorted by total error. Now, if we are running tournament selection with a tournament size of 7, if we look at, say, the bottom half of the population, those individuals with a rank below the median of total error, those individuals will receive less than 1% of all of the selections from tournament selection. So that means that if you have any specialists that are, say, not that great on total error, but are figuring out some interesting parts of the problem that are in this bottom half of the population when sorted by rank, then those individuals just aren't going to get selected much, if at all, and won't be able to propagate their interest in genetics into future generations. Even, I'm not showing it here on the slide, but even individuals, say, in the top 20%, those are receiving some huge proportion of the selections. Something like 80% of the selections go to the top 20% of the population. And so even individuals with ranks in the top, or in the top half, but not in the top, say, fifth, aren't going to receive all that many selections. Now, let's compare this to Lexicase selection. It's harder to graph Lexicase selection because it's specific to a specific population. But here I have a single population where I looked at the probability of selecting different individuals in this population. Again, this population is sorted by the total error rank. And so we're going to see that some of the individuals that have really poor total error still are being selected pretty frequently. In fact, if we'll start near the end here, we have an individual that's after index 800. So that means it's in the bottom 20% of the population that actually received almost 1% of the selections this generation for this single individual. That's about as many as tournament selection selects the best individual in the generation. And so we can see that Lexicate selection is putting a lot of emphasis on this one individual that happens to have a really poor total error. Now, even if we look at individuals that are, say, in the top half of the population, but maybe not in the top 20%, we see that we have an individual here with a rank of about 350 that actually receives the most selections, in fact, almost 5% of the selections of any individual in this generation. And more or less, if you look generally, we see a really spiky plot here because we have a lot of emphasis on some individuals that are likely good at some things and not so good at others. Some of those individuals tend to fall here in the middle. A few of those fall right here at the beginning. In fact, the first individual by total error did receive quite a few selections. That shouldn't be surprising either. But we see a lot different of a distribution of individuals that are selected. And so this gives us a lot of emphasis or of evidence for Lexicate selection selecting specialists. Now, I want to give one more piece of evidence here. And this is specifically in looking at how many training cases does Lexicate selection use in different selection events. And so these graphs here, these are histograms where the x-axis is the number of training cases that are used in a selection event across all selection events, across, I think this was across 100 runs. So there's a huge number of selection events that are included in this data from genetic programming runs. And what we see here is that many times Lexicate selection finishes, right? The peaks here are the most common locations where Lexicate selection finishes after that number of cases. So let's look at, say, the syllables problem down here in the bottom middle left. Here we see that the most frequent number of cases used when doing selection on this problem is, I think that's 5 or 6. And so that means, and we see some on each side, some use fewer cases, quite a few use more cases, up to maybe 15 or 20. We don't typically see more than 20 cases being used in any given selection event. Now, this is out of, I believe these were all using 100 cases. And so that means that even if you're using 20 cases to do a selection, it means that 80 cases you're not using. And that means that you can imagine easily individuals that perform really well on some cases, if their cases ended up coming first, they might be selected before the cases that that individual performs poorly at happen to come up in the random shuffle. Now, of course, for a different random shuffling, a different individual that may or may not be a specialist may have the best errors on the cases that happen to come up first. But we could imagine that in different Lexicate selections with different random orderings, we could get different specialists that sort of specialize in different cases being able to be selected simply because we are only looking at, on average, about, say, 5 to 15 cases per Lexicate selection event. And this means that, just as a reminder, cases that come near the beginning of the shuffled list have a lot of importance, where cases that come near the end of the shuffled list of cases have little, or in many cases, no impact on the selection. And so this gives us more evidence that specialists could be selected simply because the cases that they perform poorly at might not come up in some of the random shufflings of cases. Now, I want to move on to one, before I move on, the one important question here is that for many problem domains, in the end, we don't want a program that is a specialist. In fact, we want a program that is a good generalist, right? We want a program that passes all of our cases or gets a relatively good error across the training set. And so how do we go from selecting specialists, those that I think of, like Bill was talking about, at the corners of the Pareto front, to a good generalist program that, say, is near the knee or is very near the origin of this Pareto front? And so that's a great question that, in fact, I think could certainly use some more research in this area. There hasn't been a ton of studies here. But I think my hypothesis is specifically about, as you get better and better individuals, those individuals become better and better at larger subsets of the cases. And those individuals then, Lexicate selection is more likely to select. The more cases you perform well at, the more likely Lexicate selection is to select you. And so you could certainly imagine that over time, you get individuals that increase their specialization until they become pretty good or very good at everything, and therefore are able to sort of perform well as generalists. Okay, so now I want to change gears and look at one other important piece of the puzzle as far as Lexicate selection performance is concerned, and that is thinking about population diversity. Now, diversity in evolutionary computation, as I'm sure many of you are aware, is an important aspect of how well an evolutionary computation system can search in the search space, can identify promising regions, and then can sort of exploit those regions in order to find even better solutions. Now, when we think about diversity, here I'm going to focus on behavioral diversity. And so in this, I in particular mean the diversity of outputs across cases. So not just diversity of, say, a final value or the diversity of a genome, but specifically the diversity of the outputs or error values of the population. And so in a variety of studies, we've shown that Lexicate selection produces and maintains higher levels of this behavioral diversity. Now, if we look at these just 3 example graphs, where on the x-axis we have the generations, and on the y-axis we have population diversity, where we want higher values to indicate more diversity, what we see is that when we compare Lexicate selection to tournament selection or implicit fitness sharing, we actually get significantly higher levels of diversity in sort of across the board with Lexicate selection. And so in all 3 of these graphs, Lexicate selection is the line up near the top, where the lower lines are tournament selection and implicit fitness sharing. Now, why would that be the case? The way I think about this is that Lexicate selection selects individuals that tend to perform well at different parts of the search space. So you might select a specialist that performs well on this set of cases one time. Another selection will select an individual that performs well on a separate, different set of cases. And so those individuals are likely going to be in different areas of the search space and performing well at different subsets of your training cases. And therefore, you're going to get individuals that are sort of good at different parts of the problem, and therefore looking in different areas of the search space. This is opposed to, say, tournament selection, where if you're just optimizing your total error, you're going to get individuals that are concentrated in one area and tend to converge in order to, into a local optima. Often that might not be your global optimum, but is sort of one of the problems in something like genetic programming or genetic algorithms is that convergence to an optimum that isn't the global optimum. And so by increasing diversity, Lexicase selection is able to explore in more areas of the search space, looking for that global optimum. So this sort of can explain some of the reasons for its good performance. Now, just so that you don't worry that we've only looked at this with program synthesis, here are some results in symbolic regression problems where we looked at actually different types of Epsilon Lexicase selection. We see that Epsilon Lexicase selection maintains higher levels of diversity across the board on a variety of problems than other types of selection, including tournament selection for symbolic regression problems as well. Now, one other piece here that I find interesting is that we want to find out, okay, we see that in long-term genetic programming runs, we see high levels of population diversity with Lexicase selection. But what does Lexicase selection do on specific populations? And so we decided to do some experiments where we ran genetic programming using different parent selections starting from the exact same population. So here we actually just have 4 different populations as starting points, with different random number seeds running different selections over 20 generations. And so on the top here, we're looking at 20 generations starting from relatively high levels of population diversity. And what we find is that with Lexicase selection in gold, we see that almost every single run tends to maintain much higher levels of diversity, about where the population diversity was at the beginning of the run, where starting from those high diversity populations, tournament selection tends to quickly lose diversity over the next 5 to 10 generations, and then ends up with a lower population diversity for the remainder of the run. Now, similarly, we can look at populations that start with low levels of diversity. So in the bottom here, we have 2 populations that start with very low levels of population diversity, and looked at what happens when we run evolution from there. And again, we see that genetic programming with Lexicase selection improves diversity quickly over the next 5 to 10 generations and tends to maintain that higher level of diversity, where with tournament selection, it tends to stay at very low levels of population diversity through those next 20 generations. And so this really shows you that not only is Lexicase selection in long genetic programming runs maintaining good diversity, but it maintains good diversity when it starts with a high level of diversity, and it tends to increase diversity even when starting with a population with low levels of diversity. Now, I want to talk about one other piece of this puzzle. Now, this isn't, in fact, something that seems to help Lexicase, but it's an important thing to talk about in case you see this in the wild, and I don't want you to worry that something is broken. And this is the idea of hyperselection. Now, in both anecdotally and in sort of larger scale runs, we see that Lexicase selection often selects the same individual many times in one generation. Now, in this graph that I showed you earlier, we could say, well, it's selecting one individual almost 5% of the time, another handful of individuals over 3% of the time. And those levels of selection are much higher than any individual would be selected with tournament selection. Anecdotally, we've seen times when a single individual is selected for 50%, even 90% of the selections in a given generation. And you might wonder, isn't that going to be a problem? doesn't that sort of put a ton of emphasis on one individual? Isn't that going to do things like limit the area of the search space that evolution is searching in, and therefore lead to collapse of diversity? And so we explored this idea of hyperselection in a variety of ways, and found, surprisingly, that it doesn't seem to hurt evolution, and it doesn't seem to help evolution. And so we looked at ways of limiting hyperselection and found that even Lexicase selection with limited hyperselection works just about as well. We found that there are times when a single individual receives a lot of selections that you do see some brief drops in diversity, but because, as I just talked about, Lexicase selection is able to quickly increase diversity as well, it doesn't seem to be a problem with having low diversity. It tends to increase the diversity pretty quickly back to previous levels. And so I just want to let you know, if you see hyperselection, it is not typically something that you need to worry about. And so one other piece that we should talk about is the running time of Lexicase selection. So I'm going to pass this off to Bill in order to tell you more about that.
Great. So when we're talking about running time, the first thing that we are interested in is what is the worst case running time of this algorithm. So let's cover that first. If we have a population of n individuals, or we're doing n selections per generation, which is what we're really talking about here. Or I'm sorry, we have a population of n individuals in the pool, right? And we're also, doing n selections, then we're going to get a per generation worst case running time of n squared t. So for a single selection event with t training cases, the worst case complexity that we'll have is n times t, and that occurs when all the individuals in the population are identical. In other words, if we do the pre-selection filtering algorithm, that kind of optimization trick we talked about, this worst case running time really doesn't happen. And what we find in practice is that because Lexicase selection maintains diversity so well, it's pretty rare to observe this worst case running time. But if we look at it in comparison to tournament selection has a worst case of ONT per generation. And so that extra factor n is worse for Lexicase selection. So we have to keep that in mind. And it's something that we, would like to be able to bring down to the tournament selection level in some way or another through further research, right? If we look at this experimentally, what we observe is actually the running time of Lexicase in terms of, how long it takes for an evolutionary computation run to complete as we vary the population size. In this case, population size and the number of selections is equivalent in this system. As we vary population size, we can regress on the runtime and get an estimate of how running time varies as a function of population size. And when we look at it that way, we see that it's closer to linear in population size or number of selections than quadratic. So the kind of empirical running time that we've observed with Lexicase, in this case, Epsilon Lexicase selection, is closer to linear in running time as you would get with tournament selection, which is actually shown on this graph in circles. So empirically, the running time seems to not be as big of a problem as it is on paper for the worst case. So what about more of a theoretical treatment of the expected running time? In this case, expected running time, we mean the kind of expected running time of the algorithm, the number of steps and computational steps that are required. So under some assumptions that we have worked on a bit and are trying to understand further, we can show that the expected running time grows linearly with the population's average loss. So this is, again, making some assumptions about the population structure and how many individuals are filtered at each step. But what we're showing in this graph is how running time goes up as your average loss in your population gets better. So as the population converges, our running time linearly increases until it reaches the worst case, which is shown with the X's here. And those worst case running times are shown for different numbers of training cases, for different population sizes based on which are shown in colors. And for each of these populations that we're showing here, the point where the X crosses the line is where the entire population has reached the best possible fitness. It's all converged. Every individual is identical. And that's where we, of course, expect the worst case to be. This is work that we're very interested in and actively pursuing. And we look forward to being able to tackle some of these theoretical questions about the algorithmic complexity of Lexicase more concretely in the future. But what we know so far is that empirically, running time isn't too much of an issue. It tends to be closer to linear in the population size for the problems we've looked at. And that the expected running time is much better than the worst case running time, but assumptions required to reach those conclusions may or may not be captured in the types of problems or populations that we're looking at. So we look forward to advances in understanding this in the future. With the future in mind, let's talk about some extensions of Lexicase that have been proposed. So there's alternative ways of defining epsilon that we've looked at and others have looked at. This includes user-defined thresholds, thresholds defined using what's called madcap epsilon Lexicase, where we kind of randomly vary where that threshold epsilon is for certain selection events. There's also variants of Lexicase and epsilon Lexicase selection for survival-based algorithms, where we generate the offspring first and then have them compete with the parents, rather than using selection to choose parents and then replacing them. There's also lots of extensions that combine Lexicase with other methods, which we'll have a couple slides on here. That includes combinations with novelty search and with something called discovery of objectives via clustering. There's also extensions that look at varying how the pool starts, right? So maybe we start the selection pool not with the entire population, but with a subset, a random subset of the population. Or maybe we do Lexicase selection on islands, where those islands are defined by subsets of the population, or maybe even subsets of the training cases. So generally, these changes are just going to lower the overall selection pressure, and for certain problems that can be desirable. So a couple of these extensions that I think are really cool. The first is discovery of objectives plus Lexicase selection. So here, the idea is instead of running Lexicase on the entire error matrix as we do, where the cases are defined by training samples, why don't we first cluster those training examples, the error matrix on those training samples, into a smaller set of clusters, and then run Lexicase on those clusters. So this can have the effect of essentially combining those, let's say, modules within the problem where performance is similar or needs to be similar. And you're kind of trying to discover what those are during the run. And this is shown to perform a little bit better than just doing Lexicase selection. So
I'm going to talk about a few other extensions. One of these that has shown to work very well, specifically in program synthesis, is called downsampled Lexicase selection. In downsampled Lexicase selection, instead of using your entire set of training cases each generation, you use a subsample randomly chosen of those training cases and you only evaluate the individuals that generation on that subsample of training cases. Now, this is similar to what you might think of as mini batches used in gradient descent. And one of the big benefits here is that if you're only evaluating each program on a subsample of the training cases, that means you're using fewer program evaluations to evaluate your population. Now, this means that you can have longer evolution for the same computational cost, which could come either in the form of more generations, so you could evolve for longer evolutionary time, you could use a larger population size, or you could recoup that computational effort in some way. Or you could evolve for the same number of generations in population and have it run faster. Now, some experimental work shows that this has performed very well, even when using a very small portion of the training set, say 5 to 10% of a training set that includes, say, 100 cases. And so this sort of limit makes sense when you have, say, 5 to 10 cases. When we talked earlier about how many cases do you need for Lexicate selection to work, that seems about on the limit of what you'd expect. Now, you sort of have a trade-off here where you're evaluating each individual on fewer cases, which means you learn less information about how well they perform. And you might be missing a case where an individual performs really well on that case if you had evaluated on it. So you're losing some information per individual in this way, but you gain the fact that you're spending less effort evaluating each individual and therefore can put that into longer evolution. Now, this method, sort of downsampling combined with standard Lexicase selection has given the best performance of any selection method on the program synthesis benchmark problems that I described earlier. And so this is certainly something that is worthwhile testing. I'd love to see more data on other problem domains. This has really been only used in program synthesis. And it'd be great to see others giving this a shot as well. I'm going to tell you about, I think, 2 other extensions here of Lexicate selection. One is something that I wanted to include here because it's something that people often say to me or ask about when we talk about Lexicate selection, which is the first part of the Lexicate selection algorithm is that you shuffle the cases into a uniform random order. Now, you could imagine that maybe there's a better way of shuffling those cases, or maybe a biased way of not doing a uniform shuffle, but biasing the shuffle so that some cases tend to appear earlier more often, some cases tend to appear later more often, and therefore emphasize certain types of cases. And so we decided to experiment with this. We looked at using 3 different weighted shuffle algorithms. These are different ways of weighting your shuffling of cases. And then 9 different ways of biasing that shuffle. So using different metrics to decide which cases you might want to shuffle earlier or later. And these are things like looking at which cases is the population better at, or which cases is the population worse at. So if they have better error on that case, does the population on average have a worse error on the case? Does the population have a higher variance or a lower variance on a particular case? And I've heard different arguments, like some people think, oh, it'd be better to include harder cases, cases that the population performs worse at, earlier so that you get individuals that are performing well on these difficult cases. But I've also heard the opposite of maybe we want to include easier cases first so that we look at more different training cases, have more ties before we find an individual that outperforms the others that are remaining. Now, so we've tested a huge variety of ways of doing this biasing and this weighting of shuffling. And unfortunately, well, perhaps fortunately, none of these methods outperform a uniform shuffle. This is a bit confounding at first. You'd expect there'd be some way of doing better than a uniform shuffle, but there's actually a beauty to the uniform shuffle, which is that when you have every case equally likely to come first, that means that all of the cases are going to be emphasized equally, and that means different combinations of cases will be emphasized in different selections. That then in turn means that you're going to have higher levels of diversity because you're emphasizing different areas of the search space in different selections. And so my thought here is if you're weighting the shuffling, you're going to have lower diversity because you have more emphasis on one part of the search space than another, and therefore aren't as likely to have the high levels of diversity, or at least not as high as we typically see with Lexicate selection. The other piece of this puzzle is that perhaps you have fewer selections of specialists, at least specialists that specialize in cases that come later in the case ordering if those cases are not as emphasized. And therefore, you won't be able to have those benefits of having specialists in the population. So, I guess the good news is you don't have to implement some fancy way of biasing your shuffling. As long as you just use a uniform shuffle, you're going to get the benefits of using Lexicate selection. The last type of extension I want to talk about is combining Lexicate selection and novelty search. Now, there's some sort of theoretical reasons we might want to do something like this, such as the fact that both Lexicase and novelty search tend to emphasize diversity, tend to emphasize doing differently on certain cases. And so it turned out just by chance, two different groups came up with ways of combining Lexicate selection and novelty search in 2019. And so I'm going to tell you about both of those. In one of these, which we call novelty Lexicate selection, for each case in your list of test cases, you not only have an error value, but you also look at what are how novel is a program's output on that case. And so we assign a novelty score to each individual on each case. And therefore, we have this combination of error values and novelty scores that you can then combine as one larger pool of cases to use for Lexicate selection. Now, what we found here, interestingly, was this didn't help in the short term. So in runs around the length that we typically ran, we saw about the same performance. But when we let evolution run for longer periods of time, we found that it was able to produce higher diversity and better performance across longer stretches of evolution. I think this sort of shows that perhaps adding novelty in might make it so you don't get as much strong emphasis on improving performance early on, but in the long run, you're able to maintain higher levels of diversity and find more solutions in the long run. Similarly, let's now talk about novelty. The idea of novelty is that you're going to use novelty search for k proportion of the selections and use Lexicate selection for the other proportion, the 1 minus k proportion of the selections. And so what this means is that some of the time you're using pure novelty search and some of the time you're using pure Lexicate selection. And what the results that they found were that this works well and better than either Lexicate selection or novelty search on their own, especially if you have levels of k that are greater than 0, but maybe not more than 0.5. So maybe you're using, for example, novelty search maybe 10 or 20 or 30% of the time, and Lexicate selection the other 70, 80, 90% of the time. So in these cases, they found that performance ended up being higher, the red line here, than using just Lexicate selection, which would be at the 0 level in this graph, or just novelty search, which would be at 1.0 in this graph. And so both of these methods were interesting ways of combining the ideas of Lexicate selection and novelty search.
Excellent. So before we wrap up, I want to acknowledge all of the various authors and researchers who have made Lexicate selection such an interesting and vibrant topic of discussion. So Lee Spector, of course, Eddie Pantridge, Nick McPhee, Bill Tozier, Jason Moore, in addition to many other contributors, discussants, and reviewers that have shaped our ideas and made this a fruitful area. I'd like to thank the Epistasis Lab at University of Pennsylvania, where I work, and give a thanks to my grant support from the NIH National Library of Medicine. So in conclusion, I hope that you've enjoyed this tutorial, and what we'd like you to take away is that Lexicase selection is easy to implement. It's effective at improving performance in a number of domains, as well as improving diversity of the population during the runs in terms of their behavior. And also that it is applicable to many areas of evolutionary computation besides genetic programming where it was born. Feel free to contact us with any questions or comments. Our emails are shown below. And with that, I'll say thank you and goodbye.
Wonderful. Thank you. And thank you for watching this talk.